Right. Once more, we'll continue. So I may have forgotten some nastiness, but I think that's all the messing around with little indices and that sort of gubbins for today. So, at least in my head, what I'm trying to do now is to actually convert all those little indices and messing around into something that resembles a bit of physics, a bit of a physical picture for what's going on. So, do ask. The aim is to try and explain what some of this means. Now, yeah, this thing's run out of puff. That's the problem. Could have been charging it whilst I was talking at you. Anyway. Oh, the cursor doesn't show. So let's unplug that. Annoyances. Right. So where we finally got to was this equation, HC is EC, which looks like the Schrödinger equation, but instead of a differential equation in some continuous variables, it's a matrix equation. For instance, with two atoms, it could be a 2 by 2 matrix, being a column vector with two numbers in it, which will be how much of the different atomic solutions. Now, what it looks like is HC equals EC, and that's, in linear algebra, was an eigenvalue problem. Don't know if that rings any bells. There's a sort of, at least for smaller systems, there is a recipe for how you solve that from the determinant of H minus E. Now, what is important, once we solve this HC equals EC, if you remember what I said, the H is something we can just grind through and calculate numerically. It's not some nasty integral, but just a numerical integral of the basis functions over our Hamiltonian, things that we're in control of. An important bit here, charge this. Oh, sorry. The eigenvalues, these E values, are these energy levels for electrons in the system. So we get back to a picture we had in previous weeks, where we've got energy levels for electrons. They can be put into those energy levels, and then we can work out the system. We can see what excitations, which transitions electrons can go from one state to another. So remember this Pauli exclusion principle. So what we're going to do is we're going to calculate the energy levels, and then we're going to put an appropriate number of electrons in. Each state can only hold 2 electrons. That's one spin up, one spin down. if you remember, there was that Fermi-Dirac distribution. Okay. I will just mention this when we're doing this all the way through this course. We're going to assume that the electrons don't talk to each other. So in that sense, it's still a bit like this Drude model. So there's no electron-electron interaction. So if we look at this nice diagram here, do have a look at it forward and this interaction between the electrons is being or approximation. This is not a good approximation, but in principle we can sort of hide it away in other parameters for now. The full solution with all the electrons interacting with each other is a incredibly complicated problem. So what this means is that we can just put the electrons into the different energy levels and things don't adjust as we fill up the states or remove them. Okay, this is a lot of waffle. What it comes down to is that we've got this recipe for calculating the energy levels of a quantum mechanical system using this matrix formulation. So what I'm going to do is try and do it for a hydrogen atom from that stuff that we did. So by taking what we did an hour ago and applying it to the particular case of a hydrogen atom, we're going to see what comes out. So what we do, really wish I charged that. I've got the pointing device. So this is just a recap of what we did this morning. So wave function, approximate it as a weighted sum over the atomic orbitals. We chugged through a long-winded derivation, versus the Schrödinger equation, matrix equation, and it's a matrix eigenvalue equation. HP. Want to find the eigenvalues, they're the energy levels of the electron. If I remember, I was looking in the algebra or how to solve an eigenvalue problem, what you do is you find values of E that make this determinant of the matrix with minus lambda minus E eigenvalues on the main diagonal elements. So what we're going to do now is set up this matrix equation for a hydrogen atom, solve it, get the energy levels out, and have a quick think about what that means. So what this is going to give us is a picture of covalent bonding. So those of you that did A-level chemistry will probably have seen pictures along this sort of line. Got two atoms, two wave functions. So these individual wave functions here are going to correspond to these phi, these atomic basis functions that I drew up earlier. And what happens when they join together is somehow they interact, and there's some probability wave function extends now over both parts of it. And you can get a bonding solution. Square of it is the probability vector. And back to our week 1 lecture, it corresponds to the box getting bigger. Electrons have got more room to move, so their kinetic energy decreases, and we save energy. What we will also see is also producing next state where the electrons won't be occupying its higher end. What this actually allows us to have is optical transitions. We have additional energy levels that a photon could excite an electron from and to, so we can start to get an explanation of how materials interact with light as well. Right. So we're going to apply this matrix formulation. The way we're doing it's called molecular orbital theory, or linear combination of atomic orbitals, or tight bonding theory, tight binding theory, depending on the community you're talking to. All this stuff is a good version of it in Simon, that's quantum solid state, not in the basics or essentials, all in there. It's in the other textbooks as well. One thing I will probably skip over a little bit for now, but I will come back and try and emphasize another time, is what we're worrying about now is the electrons. We're going to assume that the atoms, the atom cores, are at some particular distance, which I'll call Rij, and there'll be some interaction between the atomic cores, but the bit we want to work out is what the energy of the electrons is when those cores are at that position. What we're going to assume, you can make it more mathematically correct, is that the nuclei are really, really heavy. They're basically stuck in place, and the electrons get to do their thing, assuming the cores just sort of sit there and provide an interaction. So, what was our recipe? The first thing was to write down the classical Hamiltonian for the system. So let's take a pair of hydrogen atoms. So, if we think about the energy of an electron, its Hamiltonian is going to be T. No idea why it's always T, but T is kinetic energy. With any quantum mechanical textbook, it's written as T, and quite often classical mechanics. I'm guessing probably the German for kinetic energy begins with T, but I don't know. Then you can tell me. But T is the kinetic energy. That's the one we've already dealt with when we did the particle in the box. It's this momentum squared divided by 2m. And then we have got V1 and V2. But remember what I was saying, this is different from the particle in the box because we've got potential energy. So, what I have got here is that the potential energies that we're going to add in. So if we've got our two atoms, two cores, and let's do hydrogen this time. So the interaction with the core, the potential energy, just looks like a Coulomb interaction. So if little r is where the electron is, and big R is where the core is, then the interaction looks like a Coulomb interaction. So if it's a hydrogen, so it's a single photon, so it carries the charge of plus E, and I'm missing one something. But the electron carries the charge of E, so it's charge of E squared, 4 pi epsilon 0, and the absolute value of the distance vector between the electron position and the core position. So that's our interaction energy of the electron with the core. If there's two cores, I've got atom 1 and atom 2, then there's two of those interactions. So total classical Hamiltonian, potential, kinetic energy, and two potential energy terms, which are coming from that interaction with the core. Right, so our approximation is going to be that the total wave function, haven't got a pointy device, is going to be sum of some amount of the wave function on atom 1, some amount of the wave function on atom 2. What's the those going to be? Those phi 1, phi 1, phi 2, their solution to the atomic problem. The atomic problem, if we scrub out atom 2 and just look at atom 1, do our normal bit, we've got that the net energy plus V1, the interaction with electron, 4-1, interacting on our atomic wave function by 1 equal to atomic wave function, the energy level on that function. And the same for atom 2. Those define our phi 2. If we actually took a real potential and solve this equation, then we could write down a functional form of it. But we're not actually going to need it here. It's just those two equations are what we need. And we're going to stick with our approximation that the two functions, two different functions, obey that equation. Yeah, orthogonal to each other. Now, this is the crux, the bit where we've got to work out these elements of this matrix. So the top right corner, I did 0 and 1, but I put it 1, 1, and I put 1 and 2 instead of 0 and 1. So if both sides, I and j, are on atom 1, I need to work out this matrix element, the Hamiltonian sandwich between phi 1 phi 1. I ignored the complex conjugate, they're going to be real. Yeah. So the way I've written it down, for the Hamiltonian, remember from the previous slide, it's the net energy plus the potential interaction 4-1 plus the potential interaction 2. Linear operators, I can split that like this. So it's P plus V1 sandwich between phi 1 and then V2 sandwich. And I'm going to call the bit on the right phi 1 V2 V cross. Call this other bit epsilon 1, the energy of the electron on the first atom. Why have I done that? Let me write this down. I've got my equation here, and we had previously said that the definition of phi 1 is that T plus V1, so that's the atom 1 Hamiltonian, acting on phi 1 equals epsilon 1 phi 1. So this is equal to the integral over all space of phi 1 epsilon 1 phi 1. So I'm substituting this in there. Now, epsilon, it's a number, it's the energy. Electron in this state. So I can take that outside the integral. So I've got epsilon 1 integral over all space of this basis function. That's equal to 1. So I'm just left with epsilon 1. So that's the top equation. So I've sandwiched H, the Hamiltonian, between the physics approximation between phi 1. I've identified it, split it up, so it's the atomic problem on atom 1 and some other term, effectively a Coulomb interaction, electron on atom 1 with atom 2, and H22, so the other element putting the electron on atom 2, exactly the same, but this time I've got the atomic problem for atom 2. And then H12, these off main diagonal elements, are completely weird quantum mechanical things that there's no obvious explanation for, but broadly speaking, very hand wavy. They talk about an electron hopping from atom 1 to atom 2. So that is our picture. We'll write them out and talk about them a bit more later. But what we get is this matrix equation. So H11 at the top is equal to energy of the atom, epsilon 1, the energy of the electron on atom 1, plus this V cross term, is the interaction with the other nuclei, and the fact with the right hand side here is 0. The off diagonal term is a strange hopping element, allows expression much lower. That's the same for both off diagonal elements, and both atoms the same type, epsilon. I can call it epsilon 1 in both cases, but for epsilon, exactly the same. And then I've got a 2 by 2 determinant that I need to solve for E, off the equation, then H V. I get 2 values of E out of the atomic energy plus this Coulomb interaction, and then plus or minus strange quantum mechanical hopping term, and the eigenvectors, which are our approximation free wave function, then is plus and minus solution, and they are our atomic solutions added in or out of phase. We'll go through this again a bit more detail, but that's the thing. The interesting point really is that we've got 2 atomic functions that we feed in. We get 2 new energy states for the system, and they come from this in and out of phase combination of the wave functions of the atoms. Let's just draw these down. So once we've solved these equations, we have got so we've got an energy level epsilon 1 on the left for atom 1. We've got energy level epsilon 2 for the second atom, but if they're the same type of atom, then they'll be the same energy. And this has got a wave function phi 1, and this has got a wave function phi 2. If we bring them, where's my hands? We bring them together and let them interact. I'll do that with a dotted line. We still find that we have two energy states, but this one is at epsilon 1 plus V 2 or V cross plus or minus T, depending on how you defined it in the first time, if T is an attractive or repulsive interval. And this one's epsilon plus V cross minus T. So they're separated by 2T. And so if we had one electron there and one electron there on each atom beforehand, so total energy initially was 2 epsilon 1 if they're the same type of atom. And the point is that now the two electrons can go into this state here, and each of those atoms has got this energy. So now energy finally is equal to 2 epsilon 1 plus V cross plus T. So if these V cross and T are negative things, they correspond to the Coulomb interaction of the electron with the other nucleus. So it will be a positive core with a negative electron. So they are going to be attractive. So we're actually going to gain energy in the system. Gain energy? I mean, the energy of the electrons will be lower in this system, but we'll have released energy into the world. And what I should have said is that the wave functions that we get out, so this one here, its solution, so we can call this phi 1, it's the best, lowest energy solution we found, and that is equal to 1 upon root 2 phi 1 plus phi 2. So it looks like this in phase combination of the two wave functions. And the other one will look like this out of phase combination of the two. So we're getting used to how this works. Right. So that was that. The final completion is that we can work out the gain in electronic energy in terms of its parameters V cross T, how much we gain by comparing the energy of the electrons when they're on the atoms with the energy of the electrons from our solutions. And then we add in any energy elsewhere in the system, in this case from the two electron cores repelling each other. And as long as the gain in energy from the electrons is more than the repulsion from the two cores, we end up releasing energy and getting a binding state of the system. Now these things in our Hamiltonian, they depend on how close the atoms are together, so how easy it is from hop from one site to the other, and what the interaction energy is with the other nucleus. So as we alter our distance, the repulsion changes, and also the binding, this interaction increases. So what we find, if we actually sort of work out some model for this system, is we're going to get something like this. As we change the distance between the two nuclei, the in-phase solution for the lower energy one will be lower in energy for the atom. Well, there's a distance, whereas the other solution is always less favorable. We've got two solutions. Now we've got an energy factor system to the photon coming in, moving electron from the state with two electrons in up to the other one, so that our system will absorb light. And when we move from two atoms to a crystal, that's how we're going to get lots of materials. So the generalization of this, where we get more filled states, more states that put electrons into, more energetically unfavorable ones that are empty. Transitions between the different ones are what allows materials to absorb light. And the chemistry diagrams, once we've got that sort of picture of these two states interacting. So the hydrogen one we talked about was one electron in each atom. So once they form this bonding level, so-called, the two electrons go into a lower energy state, and we've lowered the energy of the system, bound, and it's a nice happy molecule. If instead of hydrogens we had helium atoms, then two electrons on each of the atoms. So we now have four electrons to accommodate, so that they become not only, you have to not only fill this state, but we've got to fill this state as well. Once we work out the energy, total energy of electrons in the system, we find that we've not gained anything. That's the sort of the reason why two helium atoms don't stick together strongly. We're neglecting things like electron-electron interaction, particularly for this main thing. So hydrogen forms a nice dimer, a nice pair of this helium wouldn't. It's not just filling up this happy bonding orbital, but you've got to fill this so-called anti-banding state as well, where because of this antiphase combination, you find, in fact, you've increased the kinetic energy of these things. You've actually reduced its freedom to move around. So that is our picture of covalent bonding in terms of the quantum mechanics. It was a bit long-winded. We did extract or spend quite a bit of time working through the quantum mechanics. I'm not sure how comprehensible that was to you, sort of jumping into the quantum mechanics. But the advantage of it, something we'll see next week, is that we can move from a pair of atoms to a crystalline system, and we've got a bigger matrix that we might need a couple of tricks to figure out how to do, but nothing really changes. It's extensible, whereas other models are harder to to build on. I'll skip over that for now. So that's me waffling at you for today, pretty much. So the summary is that sort of recipe that we've got. So there are a couple of questions up on the blackboard, but I'll put a few more up probably as well, and we'll spend Wednesdays going through this, trying to put some physical intuition into this model that we've developed. But the quantum mechanics, where it came from, are these ideas of solving this Schrodinger equation, taking the classical Hamiltonian, making the transformation, which gives you this differential equation, the Schrodinger equation. And what we did this week was say we don't like solving differential equations, but we do like linear algebra. So we introduced these basic functions. So things that are varying are how much of these two functions, these atomic type orbitals that we're using to build up our wave function. So instead of a differential equation where r is varying over all sorts of things, there's just two variables that we need to optimize, just how much of orbital of function 1 and how much of function 2 in our case we need to do. And what we need to actually solve is just this 2x2 problem in this case. But as I say, on Wednesday we'll try and put a bit more physical intuition into it. We'll sort of try and talk through what's going on. But this model contains a lot more sort of physics that will help us understand properties of materials, particularly absorption of light, as well as also connecting to Drude theory. So this is essentially going to be our working model, our workhorse for understanding properties of materials going forward. Right, thank you very much for coming along. I know that was quite an involved lecture in lots of ways, lots of ideas thrown around, so try and digest it, and then on Wednesday we can talk through the different things and try and sort of firm up what some of these flying symbols and stuff mean. Okay, so I'm assuming anyone with